Assalamualaikum and welcome back. Okay, let's continue with example number 2. Here we are asked to sketch the solid bounded by 1, 2, 3, 4 equations. Then express fxyz integrate over solid G as iterated integrals in 3 different ways. So here it's it's not about evaluating the triple integral, but more on finding the iterated integrals in more than one way. Okay, let's proceed with the first part of the question, which is sketching the solid. Okay, so here our solid is bounded by 1, 2, 3, 4 equations. Well, everybody knows z equals 0. Z equals 0 is xy plane, horizontal plane, or you can sketch it like so. So here we have xy plane, horizontal plane, and y equals 0 is horizontal plane, so you can sketch it like so. So here we have y equals 0, and this is only part of it. Of course you can draw a bit larger here if you like. And we have x equals 0. So x equals 0 is another vertical plane. This is x equals 0. So here we have 3 planes, but still we don't have a solid because the surfaces are not bounded. And then of course we have another equation of a plane, which is x plus 2y plus 3z equals 6. So this is also a plane because you don't see x squared or y squared or square root in there. So it's a plane, but it's not horizontal or vertical. So it's going to be a bit diagonal. So what we're going to do is we're going to get the intersection points on the axis and then connect the points. Then we can get the plane. Okay, let's. So here we have the equation of the plane. Okay, some of you can do this very quickly. Now let's say we want to get the intersection point on the x-axis. Okay, on the x-axis, y and z are 0. So we have, because y and z are 0 on the x-axis, so we have x plus 0 plus 0 plus 0 equals 6. So too many zeros there. Okay, so we have a point which is 6, 0, 0. So we have 6, 0, 0, which is, let's say here. Okay, so that is 6. 0, 0, and then we have we need to find the intersection point on the on the y-axis. On the y-axis, x and z are 0, so we have 0 plus 2y, and here z is also 0 on the y-axis. So we have that. So from here we get y is 6 divided by 2, which is 3. So we have another point which is x 0, y 3, z 0. So maybe around here. So that is 0, 3, 0. And then we need the intersection point on the z-axis. On the z-axis, x and y are 0. So here we have x is 0, y is 0, and we have 3z is 6. So from there we get z is 2. So we have another point which is x 0, y 0, z 2. So probably here. Okay, and then you just connect the 3 points to get our plane. Okay, so here we have this point connected to that, and here we have another point. Okay, connect those, and another point, connect that. Okay, so we have a plane. So the red plane is our x plus 2y plus 3z equals 6. So here we have the intersection point on the z-axis, which is 2. Okay, so from there we get our solid. I'm gonna erase a bit. Okay, so we don't have that. Okay, so here we have our solid, which is called a tetrahedron. So this solid is called tetrahedron because it has 4 sides. Here's 1, 2, 3. Okay, the z equals 0, and then we have y equals 0, which is this, and we have x equals 0, which is this side. Okay, so and then of course the slanting bit is represented by this equation. Okay, I'm gonna erase those so that it won't be that messy. Okay, so now what we want to do is we want to express oops express f x y z integrate over solid G. Okay, I'm gonna erase this bit because some of you can do this very quickly, I'm sure. All right, for the second example I'm gonna go very slow. Okay, all right, so here we have we want to express this f x y z integrate over solid G. So our solid G is really the tetrahedron. Okay, so in this case we're gonna express this in 3 different ways. Okay, so let's look at our notes again. Remember the theorem. Okay, obviously our solid is not a cuboid. Okay, so we cannot just do the one from a constant to a constant. So let's say we want to project our solid onto the xy plane, excuse me. So we want to project this onto the xy plane. So the order of integration should be with respect to z first, and then the upper limit would be the top surface and the lower limit would be the bottom surface. Okay, so let's say we want to project our solid onto the xy plane. So if we want to do that, then our region on the xy plane would be a triangle. So like so. Okay, all right, so let me sketch our triangle, which is going to be on the xy plane. So we have on the xy plane, the region is going to be on the xy plane. So here we have the x-axis and the y-axis, and then we have the line, this line here, 6, 3. So we have on the y-axis at 3 and x-axis at 6. So here we have on the z-axis, x-axis 6 and y is 3. Okay, so here we have our region. So this is our region, which is on the xy plane. Okay, so if we do that, then our order of integration would be f x y z. We need to integrate with respect to z first. Okay, let's look at our notes again. So if this is the case, we're gonna integrate with respect to z first and then determine which is the top surface. So here, that is the top surface. That would be the upper limit, and the bottom surface would be the lower limit. It's going to be a function in terms of x and y. See here, z is lower than greater than a function k1, and then less than, and then we have function k2. Okay, now going back to our solid here. So the top, so now we need to figure out the top and the bottom surface. So here it's going to be region R on the xy plane. Okay, now we need to find what are these. Okay, the upper and the lower limits for z. Okay, now looking at your solid here, we need to figure out, so here we're gonna like putting a torchlight above the solid. Okay, and the shadow would be the projection of the solid onto the xy plane, and we already said that it's going to be this triangle here. Okay, so this triangle, this one is in 2D. Okay, now we need to figure out the top surface. So the top surface is not at 2, it's not z equals 2 because it's not a horizontal plane. So the top surface is really this red plane, the red plane, the slanting plane. Okay, and the slanting plane is governed by is governed by this equation. So that is the top surface. But then we have to figure out, we have to rewrite this so that you have z as a function of x and y. So rewriting that plane, z is equal to 6 minus x minus 2y over 3. So that would be your upper limit for z. Okay, so upper limit for z would be 6 minus x minus 2y over 3. And the lower limit, the bottom surface, would be here, the xy plane, or z equals 0. So the lower limit for z is z equals 0. Okay, so now I'm going to rewrite this. So we have our function fxyz. So the first order of integration would be with respect to z, z from 0 to the plane, which is governed by this equation, 6 minus x minus 2y over 3. Okay, now we need to figure out our dA. So dA is the area on the xy plane. So this is our region R on the xy plane. So we need to figure out whether we want to change our dA into dy dx or dx dy. I know you're very familiar with dy and then dx. So let's do that, dy and then dx. So if it's dy and then dx, x is integrated last. So x should be from a constant to a constant. Remember from double integrals? So the outer integral should be from a constant to a constant. So looking at our region here, x is going to be from 0 to 6. Okay, so lower limit for x is 0. Upper limit for x is 6. Okay, now we need to get the limits for y. The limits for y, remember from the double integral, you draw a straight line parallel to the y-axis and then figure out which is the top boundary and the bottom boundary. So the top boundary is not y equals 3 because it's not a horizontal line, it's a diagonal line, the red line here. Okay, so that's the red line. That happens when z is 0. So from you can use the plane here, because it's this line here is part of that plane. It's part of this plane, but when z is 0. So part of that plane, when z is 0, from here we get x plus 2y equals 6. And then rewriting this, you have y is 6 minus x over 2. So that would be the equation of the line. Okay, or you can also get the equation of the line here, this line, by using y equals mx plus c. Okay, and then using 2 points, one is 6, 0 and the other point is 0, 3, and from here you can get your m. M is, remember m is y2 minus y1 over x2 minus x1. So here you can get m is, you can use this one as x1 y1 and this one as x2 y2, or vice versa. Okay, let's say we have 3 minus 0, 0 minus 6, which is really negative a half. Okay, negative a half. And here, writing it back here, m is negative a half. And then you can use this point here where x is 0 and y is 3. So from there you get c is 3. Rewriting the equation, you get y is equal to negative a half x plus 3, or you can see that you can write this down as negative x plus 6 over 2, which is exactly the same as that. Okay, so it's up to you. You can get the equation of this line here by using the plane, the equation of the plane, but letting z as 0, or you can use the equation of a straight line connecting this point 0, 3 and this point 6, 0, and use y equals mx plus c, but at the end you get the same equation. Okay, alright, so the upper limit for y now would be, you can use that, or you can use this, which is 3 minus, 6 minus x over 2, and the lower limit is on the x-axis where y is 0. So this is one way of writing the iteration, the iterated integral. Okay, I'm gonna write this in a much prettier handwriting, hopefully. Okay, so that is one way where we project our solid G onto the xy plane. So the order would be to integrate with respect to z first, and then dA here, we can do it as dy dx, or you can do it the other way around, dx dy. So that is one way. Okay, so here we project our solid G onto the xy plane. All right. Okay, now I'm going to show you, well, we have to do this in 3 different ways. Okay, so let's proceed to the next one. Next way. Okay, I'm going to delete this page. Okay, so this is the second way, the second iteration. Okay, the second iterated integral. So that this one, this is the first one where we project this onto the xy plane. Okay, now the second one, let's say we want to project this onto the xy plane. So it's like putting a torchlight this way from the right hand side. So the projection of your solid would fall on the xz plane, and the iteration, we need to integrate with respect to y first, and dA here can either be dz dx or dx dz. Okay, all right, so let's back to our problem here. So now we're saying that we're projecting, it's like putting a torchlight on the right hand side. So when we do that, the solid will project onto the xz plane, which is this triangle. So it's gonna form a triangle. All right, so now I'm gonna sketch the triangle on a 2D. Okay, let's say here we have a straight line, x and z axis. So here we have, oops, x axis and z axis. Okay, let's say this is x axis, this one. Okay, and z axis here, and then we have this line. Okay, so I'm going to draw that line in 2D. So that line is, I'm going to draw it in red. Okay, so here we have 2 and 6. All right, so the one on the z axis here is 2, and here we have a 6, and yeah, this is our region R. So this is region R on the xz plane. Oh, that's ugly, don't need that. Okay, so now we want to express this integration, fxyz, integrate over solid G. But now we're going to express it in a different way. Since we project this onto the xz plane, then the order should be, we need to integrate with respect to y first. Okay, we need to integrate with respect to y first. Okay, so our region R is going to be on the xz plane, and here we have dA. Okay, so we need to integrate with respect to y first. Okay, remember here, if we project onto the xz plane, integration that we should do first is with respect to y. Now to get the upper and the lower limits for y, we have to figure out which is the right surface and which is the left surface. So the upper limit for y would be the right surface, and the lower limit would be the left surface. So it's going to be y equals a function. Okay, all right, now going back to our problem here, example number 2. So the right surface, if you do this, if you draw an arrow towards your solid, the one it crosses first would be this slanting plane. That would be the right surface, and then it will leave the solid on the y equals 0 plane. So the right surface is this plane. But then you have to rewrite it so that you have y in terms of x and z. So rewriting this, you get y is equal to 6 minus x minus 3z over 2. So that would be the upper limit for y. So upper limit for y is 6 minus x minus 3z over 2. And the left surface would be y equals 0. Okay, so let me rewrite that. So we have fxyz dy first. Upper limit is 6 minus x minus 3z over 2. Lower limit is 0. And now we need to figure out our dA. So for dA, you have to refer to this region R, which is on the xz plane. So the order here, one of them would be z first and then x. Or you can do it the other way around, x and then z. I'm going to show you z first and then x. So that would be our dA here. Alright, okay, that's ugly. I'm going to erase that bit. Okay, so now the order is z first and then x. So x is integrated last. So the one we integrated last should be from a constant to a constant. So looking at our region here, x is going to be from 0 to 6. Okay, and then we need to figure out the limits for z. So the limit for z, you look at this line here. Okay, you can use y equals, so now it's going to be z. So equation of the straight line now would be z equals mx plus c. Okay, or you can use this surface, because this line here is really part of this surface, except now y is 0. So on the xz plane, y is 0. So you can use this equation of the plane, but by letting y as 0. So that would give us x plus 0 plus 3z equals 6, because the plane now is on the xz plane where y is 0. So then you have this equation. So you can write this as z equals 6 minus x over 3, or if you like, you can put x is 6 minus 3z. But since the order is dz and then dx, so we need z in terms of x. So the upper limit for z would be, so here we draw a straight line. So the upper limit for z would be 6 minus x over 3. And the lower limit would be on the x-axis where z is 0. Okay, I'm going to rewrite that, make it prettier. So we have 0 to 6. This is for x. For z, 0 to 6 minus x over 3. And for y, 0 to 6 minus x minus 3z over 2. And here we cannot evaluate because the function is not given. We just need to get the limits for x, y, and z. Okay, another way, instead of writing this, or we can get another one. So now, let's say you want this to be dy, but then dx, dz. Okay, this is one way. That's an answer. So another one, we want dy, but then instead of dz, dx, we want it to be dx, dz. So the limits for y is still the same. It's still from 0 to 6 minus x minus 3z over 2. Now, since z is the one we integrated last, so we still refer to this sketch, the region, which is on the xz plane. So if we integrate with respect to z last, z should be from a constant to a constant. So if it's this order, z is going to be from 0 to 2. And then to get the limits for x, you still refer to this line, but then we do it this way. Okay, so it's you're looking at the right and the left boundary. So, or you can use this. Okay, so from there, from this equation, using the plane, letting y as 0 because the line is on y equals 0 plane. From here, from this equation, you can get z, x as a function of z. So x is 6 minus 3z. So x is from 0 to 6 minus 3z. So we have one more iterated integral. Okay, so we've done 3 really. One is dz, dy dx. Another is dy dz dx. And the other one is dy dx dz. But I'm going to show you one more, even though we've done 3. So another okay, another iteration is we want it to be x first. We want, okay, dt, let me rewrite this first. Okay, so the third would be we want to project this onto the YZ plane. Okay, so if we want to do that, if you refer to the theorem, the last one would be, okay, so we want to project this onto the YZ plane. The order of integration should be x first, and then your dA here can either be dy dz or dz dy. Okay, let's refer back to our problem here. Okay, so now we need to integrate with respect to x first, and here we have dA. Okay, so now we need to figure out the front and the back surface. Okay, because when you do that, looking at our solid here, if we do this, okay, then we'll see, or we'll meet this plane first. Okay, so that would be the front surface. But then you have to rewrite it as x as a function of y and z. So x here is 6 minus 2y minus 3z. So that would be the upper limit for x. 6 minus 2y minus 3z. And the back surface would be this plane, which is on the YZ plane where x is 0. Okay, now we need to figure out dA, which is a region on the xy plane. So it's really just the YZ plane. So here we have YZ plane, and we have a triangle. Okay, so here we have a triangle, 3 on the y-axis and 2 on the z-axis. Okay, all right, so now the order of integration is up to you. You want it to be dz dy or dy dz. Okay, let me rewrite this first. Okay, so y is from 0 to 6 minus 2y minus 3z. Okay, now let's look at our dA. One way would be, sorry, it should be x there. Copy it wrong. Alright, so it should be x dx. Okay, so now your dA here, it can be write that as dz dy, or the other way around, dy dz. Okay, let's say we want it to be dz and then dy. So if that is the case, y is integrated last, so y should be from a constant to a constant. So you just refer to this triangle here. Y is from 0 to 3. And now we need to figure out the limits for z. Okay, so you can use the equation z, the straight line equation. Z equals, now it's going to be my plus c. Or you can use this plane here, because this plane on the YZ plane is right here. That's the same line as this. But then on this plane, on the YZ plane, x is 0. So rewriting that, when x is 0, you get 0 plus 2y plus 3z equals 6. And then you can write z as a function of y. So z is going to be 6 minus 2y over 3. Or you can write y as a function of z. So y is going to be equal to 6 minus 3z over 2. So both of them represent this line. Okay, alright. So if we write it as dz and then dy, so we're going to use this equation. So it's going to, oops, it's going to be 6 minus 2y over 3, and lower limit is 0. Or another way would be fxy dx dy dz. So if it's dx dy dz, so here y, the limits for x is still the same, 0 to 6 minus 2y minus 3z. But then if it's dy dz, z is integrated last, so should be from a constant to a constant from this triangle. Z is going to be from 0 to 2, but the limits for y excuse me, you're going to use this straight line. Okay, it's the same straight line, but we're going to use this equation. So y is going to be from 0 to 6 minus 3 z over 2. So here we have 4 iteration, really. Okay, 1, 2, and here we have 3, 4 iteration. Oh, and one more here, which is, so we have 5 iteration. Instead of 3, we come up with 5 iterations. Okay, so I'm sorry I took a longer time to solve, to explain example 2, because this is the basic concept of finding the limits of x, y, and z, and also where you want to project your solid G onto. So in this example, our solid is a tetrahedron, so you can project this onto the xy plane, yz plane, or xz plane. You have 3 choices there. So we have many iterated integrals for this. Okay, that's all for example 2. Thank you.